What if I told you that right now, at this very moment, one of the brightest stars you can see in the night sky is doing something so bizarre, so completely unexpected, that astronomers are scrambling to rewrite decades of stellar physics? And here's the kicker. What's happening to Betelgeuse might already have happened. In fact, this star might have already exploded, and we just don't know it yet. Picture this. It's December 2019, and astronomers around the world are staring at their telescopes in disbelief. Betelgeuse, the massive red supergiant that forms the shoulder of Orion, has suddenly dimmed by more than 60%. That's not a typo. 60%. For a star that's been relatively stable for thousands of years, this is astronomical pun intended. The internet explodes with speculation. Is this it? Is Betelgeuse about to go supernova? Could we wake up tomorrow to a second sun in our sky? But here's where it gets absolutely mind-bending. What happened next wasn't what anyone expected. Not the professional astronomers with decades of experience. Not the supercomputer models running millions of simulations. Nobody. And what we've discovered since then has opened up questions that are fundamentally changing our understanding of how massive stars die, what happens in their final moments, and whether we've been wrong about stellar evolution this entire time. Here's what will blow your mind. Betelgeuse isn't just one mystery. It's a Russian nesting doll of mysteries, each one more profound than the last. The dimming event? That was just the beginning. Since then, we've detected pulsations that shouldn't exist, surface features that defy physics as we know it, and behavior that suggests something is happening deep in the core of this star that our models simply cannot explain. And the stakes? They couldn't be higher. Betelgeuse is only 650 light-years away. In cosmic terms, that's our backyard. When this star goes supernova, and it will be the most spectacular celestial event in recorded human history. It will be visible during the daytime. It will cast shadows at night. It will be brighter than the full moon. And depending on what we're now learning about its behavior, the timeline for this event might be very different than we thought. But before we hit that subscribe button, I need you to do something for me. Drop a like on this video right now. Seriously. Because what you're about to learn over the next few hours is going to fundamentally change how you look at the night sky. And I want you to tell me in the comments, what country are you watching from? And what time is it where you are? Because when Betelgeuse does finally explode, it won't matter what time zone you're in, the entire planet will witness it together. We'll all be united under that new light in the sky. So hit that subscribe button, ring the notification bell, because this story is still unfolding and you're going to want to be here when the next chapter breaks. Now, let me take you back to where this story really begins. Not in 2019, but much, much earlier. Because to understand what's happening to Betelgeuse now, we need to understand what Betelgeuse actually is. And trust me, even the basics of this star are anything but basic. Betelgeuse is what astronomers call a red supergiant. But those words don't do justice to the sheer, incomprehensible scale of what we're talking about. Think of it like this. If you placed Betelgeuse where our sun is right now, its surface would extend beyond the orbit of Mars. Jupiter might be skimming its outer atmosphere. That's not a star. That's a stellar monster. We're talking about something so massive that if you could hollow it out, you could fit more than 1 billion suns inside it. 1 billion. Here's another way to wrap your head around this. Light, which travels at 186,000 miles per second, takes about 8 minutes to get from the sun to Earth. If light started at the center of Betelgeuse and traveled to its surface, it would take over an hour. A photon born in the core of our sun struggles for thousands of years to reach the surface, but that's because of density and absorption. With Betelgeuse, we're just talking about raw distance. The star is so big that its surface is an hour of light travel away from its core. But size isn't what makes Betelgeuse special. Well, not just the size. What makes Betelgeuse truly extraordinary is what it represents. A star in its death throes. And not just any death, a violent, catastrophic, universe-altering death. You see, stars like our Sun will die relatively peacefully. In about 5 billion years, the Sun will swell into a red giant, gently shed its outer layers, and settle down as a white dwarf, essentially a stellar ember that will slowly cool over trillions of years. It's the stellar equivalent of retiring to Florida and peacefully fading away. But Betelgeuse? Betelgeuse is going out in the most spectacular explosion the universe can produce, a supernova. And not just any supernova, a Type 2 supernova, the kind that only massive stars can produce. When Betelgeuse explodes, it will, for a brief moment, outshine an entire galaxy. It will forge elements that have never existed in that part of space. It will send shockwaves rippling through the interstellar medium for thousands of light years. It will quite literally change the cosmic landscape. Now here's where we need to talk about stellar evolution, because this is crucial for understanding why what's happening to Betelgeuse is so weird. Stars are basically battles between two fundamental forces: gravity, which wants to crush everything inward, and fusion, which pushes everything outward. For most of a star's life, these forces are in balance. The star is stable. Our Sun, for instance, has been steadily fusing hydrogen into helium in its core for about 4.6 billion years. This process releases energy, which creates pressure, which pushes outward against gravity's inward crush. Balance, stability. The Sun will keep doing this for another 5 billion years or so, as predictable as clockwork. But massive stars like Betelgeuse live very different lives. They burn through their fuel fast, really fast. While our Sun will live for about 10 billion years total, a star with Betelgeuse's mass might only live for 8 to 10 million years. Think about that ratio. If you compress the Sun's lifetime into a single human lifetime of 80 years, Betelgeuse would live for about 2 months. And those last days? Those last days are absolutely wild. Here's what happens. The star starts by fusing hydrogen into helium, just like the Sun. But when the hydrogen in the core runs out, something remarkable happens. The core contracts, heats up, and starts fusing helium into carbon and oxygen. Then, when the helium runs out, the core contracts again, heats up more, and starts fusing carbon. Then neon, and oxygen. Then silicon. Each stage is shorter than the last. The star might spend millions of years fusing hydrogen, thousands of years fusing helium, a few years fusing carbon, months fusing neon, a single day fusing silicon. And here's the kicker. Each stage creates a new layer. By the time the star is in its final phase, it's like an onion, with different elements fusing in different shells. Iron core in the center, surrounded by silicon, sulfur, oxygen, carbon, helium, and hydrogen layers, each one burning at a different rate. But then the star hits a wall, a fundamental physics-based wall. It starts producing iron in its core. And here's the thing about iron. You can't fuse iron and get energy out. Iron is the most stable nucleus. Fusing iron actually costs energy. So when the core becomes pure iron, the star's energy source suddenly shuts off. The outward pressure vanishes, and gravity wins. What happens next happens fast, unbelievably fast. In less than a second, literally faster than you can blink, the core collapses. The iron core, which might have been about the size of Earth, collapses down to a sphere, maybe 20 kilometers across. The density becomes so extreme that protons and electrons are crushed together into neutrons. And then, in one of the most violent events in the universe, the collapse stops, the core rebounds. A shockwave tears outward through the star at a significant fraction of the speed of light, and the star explodes. That's a supernova. That's what's waiting for Betelgeuse. That's the cosmic time bomb sitting in the shoulder of Orion. Now, for decades, astronomers thought they had a pretty good handle on when this might happen. Based on the star's mass, its size, its temperature, and its position in the Hertzsprung-Russell diagram, basically a plot of stellar temperature versus brightness. They estimated that Betelgeuse had maybe 100,000 years left, maybe more, maybe less, but definitely not something we needed to worry about in human timescales. But then came December 2019, and everything changed. The dimming event of 2019 to 2020 wasn't just dramatic, it was unprecedented. Between October 2019 and February 2020, Betelgeuse's brightness dropped by a factor of about 2.5. In magnitude terms, that's about one full magnitude from magnitude 0.5 to magnitude 1.6. To put that in perspective, imagine if the moon suddenly dimmed by the same amount. You'd notice. Everyone would notice. Ancient civilizations would have absolutely freaked out. And modern astronomers did freak out, because they had no idea what was happening. Was the star about to explode? Was this the beginning of the end? Observatories around the world pointed their instruments at Betelgeuse. Space telescopes adjusted their schedules. Amateur astronomers with backyard telescopes monitored it every clear night. The astronomical community held its collective breath. Miguel Montargis, an astronomer at the Paris Observatory, led one of the key observational campaigns. Using the Very Large Telescope in Chile, which, despite its hilariously uninspired name, is one of the most powerful ground-based telescopes on Earth, his team captured unprecedented images of Betelgeuse's surface during the dimming event. And what they saw was stunning. The star's surface wasn't dimming uniformly. Instead, a huge dark region had appeared in the southern hemisphere of the star. It looked like someone had taken a giant bite out of Betelgeuse. The images showed that about a quarter of the star's visible disk had become significantly darker than the rest. Here's where the first major aha moment happened. Montargis and his team proposed that Betelgeuse had experienced something called a surface mass ejection, essentially a stellar tantrum. The star had belched out a huge cloud of material from its surface. This material cooled, condensed into dust, and formed a cloud that was blocking our view of part of the star. It was like Betelgeuse had blown a smoke ring at us, and we were watching it from the side. Think of it like this. Imagine you're looking at a streetlight on a foggy night. Now imagine someone next to the streetlight suddenly releases a huge puff of smoke. From your perspective, the streetlight would appear to dim as the smoke passes in front of it. That's essentially what happened with Betelgeuse. The star hadn't actually dimmed our view of it, had just been partially blocked by a cloud of stellar smoke. This seemed to explain the observations. As the dust cloud dispersed over the following months, Betelgeuse brightened again. By April 2020, it was back to its normal brightness. Crisis averted. Mystery solved, right? Wrong, because here's what nobody expected. The dust cloud explanation, while elegant and seemingly complete, raised more questions than it answered. For one thing, the sheer amount of material that Betelgeuse would have needed to eject to create that dust cloud was staggering. We're talking about a mass equivalent to several times the mass of the moon, expelled from the star's surface in a relatively short period of time. That's not normal stellar behavior. That's not something our models predicted massive stars did, especially not stars that weren't immediately about to explode. Andrea Dupree, an astronomer at the Harvard-Smithsonian Center for Astrophysics, took a different approach to studying the dimming event. She used data from the Hubble Space Telescope, which had been monitoring Betelgeuse's ultraviolet light. And what she found added another layer to the mystery. Dupree's team discovered that before the visible dimming event, Betelgeuse had experienced a massive convective plume, a bubble of hot material from deep within the star that had risen to the surface. When this plume reached the surface, it cooled and ejected material into space. This material condensed into dust, creating the cloud that caused the dimming. But here's the kicker. The convective plume itself was enormous, about a quarter of the star's radius. And the fact that such a massive convection cell could form and reach the surface suggested that something very unusual was happening inside Betelgeuse. To understand why this is so significant, we need to talk about convection. Think of it like this. When you heat water in a pot, hot water at the bottom rises, cools at the top, and sinks back down, creating a circulation pattern. Stars do the same thing, but with plasma instead of water, and on scales that are hard to comprehend. In our sun, these convection cells are relatively small, maybe 1,000 kilometers across. We can see them as granulation on the sun's surface. But in a red supergiant like Betelgeuse, the convection cells are huge. We're talking about cells that might be larger than the orbit of Mercury. And these cells are moving at speeds of tens of kilometers per second, carrying vast amounts of material from the star's interior to its surface and back again. It's like the entire star is boiling, with bubbles the size of planets rising and falling through the stellar atmosphere. What Dupree's observations suggested was that one of these convection cells had been particularly massive and energetic. When it reached the surface, it didn't just rise and sink back down. It was so energetic that it ejected material right off the star's surface. That material cooled, condensed into dust, and blocked our view of part of the star. But here's what will blow your mind. If this explanation is correct, then the dimming event we observed wasn't a sign that Betelgeuse is about to explode. It was a sign of something else, entirely something that suggests Betelgeuse's internal structure is far more chaotic, far more dynamic, and far more unpredictable than we ever imagined. And that's where we get to the real mystery. Because since that dimming event, Betelgeuse has continued to behave strangely. Its brightness has been oscillating in patterns that don't match our predictions. Its surface features are changing on timescales that seem too rapid. And most intriguingly, recent observations suggest that Betelgeuse's pulsations, regular expansions, and contractions that most red supergiants exhibit have become irregular, or possibly even stopped. Now, before we dive deeper into these recent mysteries, I want you to pause and think about what we've just covered. We've gone from basic stellar structure to the mechanics of supernova explosions to cutting-edge observations of a dying star. Can you feel the progression? We're building a foundation here, because what comes next is going to get wild. The observations we're about to discuss are so new, so unexpected, that astronomers are still trying to figure out what they mean. But first, let me ask you this. Have you subscribed yet? Because this video is already getting long, and we're just getting started. The next sections are going to dive deep into the cutting-edge research, the competing theories, and the implications of what's happening to Betelgeuse. And trust me, you don't want to miss it. So if you haven't already, hit that subscribe button right now. Tell me in the comments, what's the most surprising thing you've learned so far? And are you ready to go even deeper? Now, let's talk about pulsations. Because this is where the Betelgeuse mystery takes a turn that nobody saw coming. Most red supergiant stars pulsate. They expand and contract regularly, like cosmic hearts beating in the darkness. These pulsations are driven by processes in the star's outer layers. Basically, the star becomes unstable to certain types of oscillations, and it rings like a bell in slow motion. For Betelgeuse, astronomers had long observed a primary pulsation period of about 400 days. The star would brighten, dim, brighten again, like clockwork. Or at least like stellar clockwork, which is pretty darn reliable. But here's where things get weird. Really weird. In late 2020, astronomers noticed that Betelgeuse's pulsation pattern had changed. The 400-day period seemed to have vanished, or at least become much less prominent. Instead, the star was oscillating in different ways, with different periods, none of which matched the historical data. Jared Goldberg, a postdoctoral researcher at the Flatiron Institute in New York, has been studying Betelgeuse's recent behavior in detail, and his findings are genuinely puzzling. According to Goldberg's analysis, Betelgeuse might have experienced what's called pulsation mode switch. Essentially, the star changed its tune. Instead of pulsating in its usual mode, it started pulsating in a different mode, or possibly multiple modes at once. Now, Why would a star change its pulsation pattern? That's the million-dollar question. One possibility is that the dimming event, that massive mass ejection we talked about earlier, was so violent that it literally changed the structure of the star's outer layers. Imagine throwing a rock into a still pond. The rock creates ripples that spread out across the surface. But now imagine throwing a rock so large and so violently that it changes the depth of the pond in one area. The wave patterns would change. They'd be different. That might be what happened to Betelgeuse. But there's another, more unsettling possibility. What if the change in pulsation is coming from deeper inside the star? What if something fundamental is changing in Betelgeuse's core, and we're seeing the effects ripple outward through the star's layers? If this is correct, then Betelgeuse might have tens of thousands of years left before it explodes, not hundreds or thousands. The star might not be as close to death as we feared. The dimming event, the pulsation changes, all the weird behavior, it might not be a sign of imminent explosion, but rather just normal, albeit dramatic, behavior for a star of this type. But here's where it gets complicated. Not everyone agrees with these conclusions. Other astronomers, using different data and different models, come to different conclusions. Some still think Betelgeuse is very close to exploding. Others think it has a long time left. The truth is, we're still figuring this out. The data is complex. The star is behaving unpredictably, and our models have significant uncertainties. This is actually a perfect example of how science really works. In popular media, science is often portrayed as a steady march toward truth, with each discovery building neatly on the last. But real science is messy. It's full of contradictions, competing theories, uncertain data, and scientists who disagree with each other. And that's okay. That's actually healthy. It means we're pushing at the boundaries of knowledge, exploring territories where the answers aren't clear yet. The Betelgeuse mystery is a case study in this process. We have observations that show something weird is happening. We have multiple theories trying to explain those observations. We have different research teams using different methods and coming to different conclusions. And gradually, through this messy, contentious, collaborative process, we'll converge on a better understanding of what's really going on. But let me throw another curveball at you. What if Betelgeuse isn't alone? What if it has a companion star? Now, this is speculative. There's no direct evidence of a companion star around Betelgeuse. But it's not a crazy idea. Many massive stars exist in binary or multiple star systems. In fact, it's quite common. And a companion star could potentially explain some of Betelgeuse's weird behavior. Here's how. If Betelgeuse has a smaller companion star orbiting it, that companion could be stirring up Betelgeuse's outer layers through tidal interactions. The gravitational pull of the companion could create asymmetries in Betelgeuse's structure, trigger enhanced mass loss, and generally make the star's behavior more chaotic. The companion could also be accreting material from Betelgeuse's stellar wind, which could create additional observable effects. The problem is detecting such a companion. If it exists, it would be vastly fainter than Betelgeuse itself. It would be like trying to see a candle next to a searchlight. And Betelgeuse is so large and bright that it would completely overwhelm any light from a companion star in most observations. But there are ways to look. Future observations with advanced interferometers might be able to detect the gravitational influence of a companion, even if the companion itself can't be seen directly. Precise measurements of Betelgeuse's motion through space might reveal a wobble caused by orbiting another star. Long-term monitoring of the star's brightness might reveal periodic variations that could indicate an orbiting companion. If a companion is discovered, it would completely rewrite our understanding of Betelgeuse's evolution and future. Binary systems evolve differently than single stars. The companion could strip material off Betelgeuse, altering its mass and evolution. When Betelgeuse eventually explodes, the companion would be affected too. Possibly, it would be destroyed or ejected from the system at high speed, or it might survive and remain in orbit around the neutron star or black hole that Betelgeuse leaves behind. This is the thing about astronomy. Every answer raises new questions. Every discovery opens new avenues of investigation. And Betelgeuse, for all that we've learned about it, is still full of mysteries. Now let's talk about what happens when Betelgeuse actually explodes, because this is where things get really exciting. We've been dancing around the supernova itself, but let's dive deep into what that event will actually be like. When Betelgeuse's core collapses and rebounds, sending a shockwave tearing through the star, that shockwave will take hours to reach the star's surface. Remember, the star's huge light takes over an hour to cross from center to edge. So even though the core collapse happens in less than a second, the visible explosion takes time to develop. The first sign we'll see is a sudden brightening in neutrinos. Neutrinos are ghostly particles that barely interact with matter. They're produced in vast numbers during a core collapse, and they escape the star immediately, unlike light, which has to work its way through the stellar material. Neutrino detectors on Earth, huge tanks of ultra-pure water buried deep underground, will detect a surge of neutrinos from Betelgeuse several hours before we see the optical explosion. This is huge. This is incredible. When the neutrino detectors go off, astronomers will know Betelgeuse is exploding right now. They'll point every telescope on Earth toward Orion. They'll scramble to get observing time on space telescopes. They'll alert the amateur astronomy community, and then they'll wait, watching for the light of the explosion to become visible. And oh, what a sight it will be. As the shock wave breaks through Betelgeuse's surface, the star will begin to brighten rapidly. Within hours, it will be brighter than any star in the night sky. Within a day, it could be as bright as the full moon. At its peak, which will last for weeks to months, it will be visible during the daytime. You'll be able to see it in broad daylight, a brilliant point of light in the sky. Think about that for a moment. When's the last time you could see a star during the day, besides the sun? Venus sometimes, if you know exactly where to look. But this will be unmistakable. It will be the second most prominent object in the sky. Children will point at it. News organizations will cover it. It will be a global event, impossible to miss. And the color. Supernova go through different color phases as they evolve. Initially, Betelgeuse's supernova will be blue-white, intensely hot and brilliant. As it expands and cools, it will shift toward yellow, then orange, then red. The expanding debris cloud will create a nebula that will remain visible for thousands of years, a monument to the star that was. Now, here's a question I know you're wondering about. Is Betelgeuse's supernova dangerous to Earth? The short answer is no. At 650 light-years away, Betelgeuse is far enough that the supernova won't pose any direct threat. The radiation will arrive as light, intense light, yes, but not enough to harm us. We won't be bathed in deadly gamma rays or X-rays. Our atmosphere will protect us from any high-energy particles. However, there could be subtle effects. The increased light in the night sky could affect ecosystems that depend on darkness. Nocturnal animals might be confused. Some species of birds that navigate by the stars might have their migration patterns disrupted. And there might be minor effects on Earth's upper atmosphere from the increased UV radiation, though nothing dangerous. But the real impact will be cultural and psychological. Humans will look up and see something that hasn't been seen since 1604, when Kepler's supernova appeared. We'll witness a cosmic event that our ancestors could only imagine. And we'll do so with scientific instruments that can probe every detail of the explosion, from the neutrinos it produces to the chemical composition of the ejected material. Scientists will study this supernova intensely. They'll measure its brightness over time, creating a light curve that can be compared to models. They'll analyze the spectrum of light, looking for the signatures of different elements and measuring velocities of the expanding material. They'll watch for the formation of a neutron star or black hole in the remnant. They'll study how the supernova ejecta interacts with the circumstellar material we talked about earlier. And here's something cool. The supernova will be so bright that amateur astronomers will be able to contribute meaningful observations. You won't need a giant telescope or expensive equipment. A simple backyard telescope, or even binoculars, will be able to see incredible detail. Amateur astronomers around the world will monitor the supernova nightly, providing data points that professional astronomers can use in their research. It will be a moment of citizen science on a global scale. School children will observe it as part of their science classes. Amateur astronomy clubs will host public viewing events. People who have never looked through a telescope before will be inspired to do so. The Betelgeuse supernova could spark a renaissance in public interest in astronomy, inspiring a new generation of scientists and space enthusiasts. But here's something that I find deeply moving about this whole situation. We are living in a unique moment in human history. For the first time ever, we have the knowledge and the tools to anticipate a nearby supernova, to understand what's happening, and to study it in exquisite detail when it occurs. Our ancestors saw supernova as omens, signs from the gods, terrifying disruptions of the cosmic order. We see them as natural phenomena, endpoints of stellar evolution, factories for creating heavy elements. Yet even with all our scientific knowledge, there's still a sense of awe, of wonder, of excitement about the prospect of seeing Betelgeuse explode. We haven't lost the capacity to be amazed by the universe. If anything, knowing more makes it more amazing. Understanding the physics behind a supernova doesn't diminish the spectacle, it enhances it. Knowing that we're watching the final chapter of a star's life story, that we're witnessing the birth of a neutron star, that we're seeing elements being forged and scattered into space, all of that makes the event more meaningful, not less. And that brings me to a question I want you to think about. What does it mean to witness something like this? What does it mean to be present for a cosmic event that happens once every few hundred years in a given galaxy? What does it mean to be alive at a time when humanity has the knowledge to understand what we're seeing? I don't have a definitive answer to that question, but I think it means we're participants in something larger than ourselves. We're part of a cosmic story that's been unfolding for billions of years. We're brief flickers of consciousness in a vast universe, but we're flickers that can look up, observe, understand, and appreciate. We can know that we're made of stardust literally. The atoms in our bodies were forged in stars like Betelgeuse and scattered by supernova explosions. We are the universe experiencing itself. And when Betelgeuse explodes, we'll be watching one of our cosmic relatives die and be reborn as something new. The iron, nickel, silicon, oxygen, and countless other elements created in Betelgeuse's core and ejected by the supernova will eventually be incorporated into new stars, new planets, maybe even new forms of life. Nothing is wasted in the universe. Everything is recycled. Death and birth are intertwined on cosmic scales. So when you look up at Betelgeuse, when you see that reddish star twinkling in Orion's shoulder, remember, you're looking at a dying star, a cosmic titan in its final years or centuries or millennia. You're looking at a future supernova. You're looking at a forge where heavy elements are being created. You're looking at something that has been shining for millions of years and will soon, in astronomical terms, cease to exist as a star and become something else entirely. That's humbling. That's profound. And that's why the Betelgeuse mystery matters. It's not just about understanding stellar physics. It's about understanding our place in the cosmos. Now, before we move on to the next section, I want to ask, are you still with me? We've covered a lot of ground. We've gone from basic stellar structure to supernova physics to the cutting-edge observations of Betelgeuse's weird behavior. We've talked about dimming events and pulsations and surface features and circumstellar envelopes. We've explored competing theories and unsolved mysteries. And we've connected it all to the bigger picture of what it means to be human in a universe of dying stars. If you're still watching, drop a comment and tell me, What's been the most mind-blowing revelation so far? What's the one thing that made you pause and think? And are you ready for the next layer of this mystery? Because we're about to go even deeper. We're going to talk about what Betelgeuse can teach us about other stars in the galaxy, about supernova progenitors, about the fate of massive stars in general. The story of Betelgeuse is really the story of stellar evolution writ large, and understanding this one star helps us understand thousands of others. So stick around, keep watching, and let's dive into the next chapter of the Betelgeuse mystery. One of the most fascinating aspects of studying Betelgeuse is that it's not just one data point, it's a Rosetta Stone for understanding an entire class of stars. Red supergiants are relatively common in the universe, but they're also relatively short-lived in cosmic terms, so catching one in the act of doing something interesting is rare and valuable. Think about it this way. We've observed a lot of supernova over the years, hundreds of them. But in almost every case, we had no idea the star was about to explode until it actually exploded. We didn't get to study the progenitor star in detail. We couldn't watch the lead-up to the event. We just saw a star that wasn't there before suddenly appear, brighten, and then fade away over weeks or months. But with Betelgeuse, we're watching a potential supernova progenitor in exquisite detail. We can see changes happening in real time. We can study the star's surface, its atmosphere, its circumstellar environment. We can track its pulsations, its mass loss, its dimming events. And when, not if when, Betelgeuse does eventually explode, we'll have a complete record of what the star was doing in the years, decades, and centuries before the explosion. That's unprecedented. That's the kind of data that can validate or invalidate entire theories about stellar evolution. It's the kind of data that can tell us whether our models of supernova progenitors are accurate or whether we've been missing something fundamental. And what we're learning is already challenging some of our assumptions. For example, the Great Dimming Event of 2019 to 2020 showed that red supergiants can experience massive, violent outbursts years or decades before exploding. Our models didn't really predict this. Some models suggested small fluctuations in brightness, but nothing on the scale of what we observed. Now astronomers are asking, how common are these outbursts? Do all red supergiants experience them, or just some? Are they triggered by specific conditions in the star's interior? Or are they random? And most importantly, are they a sign that the star is close to exploding, or just normal behavior for stars in this evolutionary phase? To answer these questions, astronomers are studying other red supergiants more carefully. They're looking for similar dimming events, pulsation changes, and other anomalies. And they're finding them. It turns out Betelgeuse isn't alone in its weird behavior. Other red supergiants also show variability, surface features, mass loss episodes, and irregular pulsations. Betelgeuse might just be the most dramatic example, or the one we've studied most carefully, but it's part of a pattern. This is leading to a revised picture of red supergiant evolution. Instead of seeing these stars as relatively stable objects that quietly burn through their fuel before exploding, we're starting to see them as dynamic, turbulent, unpredictable objects that experience violent episodes throughout their lives. The final years or decades of a red supergiant's life might be characterized by increasing instability, with outbursts becoming more frequent and more violent as the star approaches its end. If this picture is correct, then we might be able to identify supernova progenitors before they explode by looking for these telltale signs of instability. We might be able to say, this star is dimming unexpectedly. Its pulsations are changing. It's ejecting large amounts of material, watch this one. It might go supernova soon. That would be a huge advance in supernova prediction, moving us from this star will probably explode sometime in the next 100,000 years to this star might explode in the next 100 years. And speaking of supernova prediction, let's talk about one of the most exciting developments in Betelgeuse research, the use of 3D computer simulations to model the star's interior in unprecedented detail. Traditional stellar models treat stars as if they're perfectly spherical and symmetric. Everything depends only on the distance from the center. This is a reasonable approximation for most stars, most of the time. But for a star like Betelgeuse, with its massive convection cells, its asymmetric surface features, its pulsations and outbursts, the spherical approximation breaks down. Enter 3D hydrodynamic simulations. These are computer models that simulate the star's interior in 3 dimensions, allowing for asymmetries, turbulence, convection, and all the messy, complex physics that happens in a real star. These simulations are computationally expensive. They require supercomputers running for weeks or months to simulate just a few years of stellar evolution. But they're giving us insights that we could never get from traditional models. For example, 3D simulations have shown that convection in red supergiants is much more chaotic than we thought. The convection cells aren't just smooth, steady flows of material rising and falling. They're turbulent, with vortices, eddies, and shock waves forming and dissipating. Material doesn't just rise to the surface and sink back down. It can be thrown off the star entirely, contributing to mass loss. These simulations are also helping us understand Betelgeuse's dimming event. By simulating the formation and evolution of convective plumes, researchers can show how a particularly large and energetic convection cell could reach the surface, eject material, and create the dust cloud that blocked our view of part of the star. The simulations even reproduce some of the asymmetries we observed in Betelgeuse's brightness during the dimming event. But here's what really excites me about these simulations. They're giving us a window into the star's interior. We can't see inside Betelgeuse directly. The star's outer layers are opaque. But by running simulations that match the observed surface behavior, we can infer what must be happening deeper inside. We can see which burning shells are active, how material is flowing between layers, where instabilities are developing. It's like doing an MRI of a star. We can't physically probe the interior, but we can create detailed 3-dimensional maps of what's happening inside based on what we see on the surface. And what these simulations are revealing is that the interior of a red supergiant like Betelgeuse is far more complex than we ever imagined. There are multiple burning shells, each with its own dynamics. There are convective regions that penetrate between layers, mixing material in ways that violate the neat, stratified picture we had before. There are oscillations and instabilities that can trigger sudden changes in the star's behavior. This complexity is part of why predicting exactly when Betelgeuse will explode is so difficult. The star isn't a simple, predictable system. It's a complex, chaotic system where small changes in initial conditions can lead to large differences in outcomes. It's the stellar equivalent of the butterfly effect. But even chaos has patterns. And by studying enough red supergiants, by running enough simulations, by collecting enough data, we're starting to identify those patterns. We're learning what the warning signs of an imminent supernova look like. We're narrowing down the range of possible behaviors. We're getting better at reading the stellar tea leaves. Now let's shift gears and talk about something that doesn't get discussed as often, but is absolutely crucial. The role of rotation in red supergiant evolution. Stars rotate. Our sun rotates once every 25 days or so at its equator. Some stars rotate much faster, completing a rotation in hours or days. Others rotate much slower, taking months or years for a single rotation. Rotation affects stellar evolution in profound ways. A rotating star isn't perfectly spherical. It bulges at the equator due to centrifugal force. This changes how material moves inside the star, affecting convection patterns and burning rates. Rotation also generates magnetic fields through a process called the dynamo effect, and those magnetic fields can channel material, create stellar winds, and drive mass loss. For Betelgeuse, rotation is complicated. The star itself is rotating slowly, with a rotation period of several decades. But here's the thing. Betelgeuse is so massive and extended that different parts of the star might be rotating at different speeds. The core could be rotating faster than the envelope. Different convection cells could be rotating at different rates. The star might not even be rotating as a rigid body. Instead, different regions might be slipping past each other. This differential rotation can create shear zones where material moving at different speeds rubs against itself. These shear zones can be unstable, generating turbulence and mixing. They can also generate magnetic fields, which can affect the star's mass loss and drive stellar winds. Some researchers have suggested that Betelgeuse's unusual behavior, the dimming events, the pulsation changes, the asymmetric surface features, might be partly explained by complex rotation patterns in the star's interior. Maybe a rapidly rotating core is affecting the overlying layers. Maybe differential rotation is driving enhanced mass loss from certain regions of the star's surface. The problem is, measuring a red supergiant's rotation is incredibly difficult. The star is so large and so far away that we can't see it rotating directly. We have to infer the rotation from subtle effects like Doppler shifts in spectral lines or from the shapes and patterns of surface features. And for a star as chaotic as Betelgeuse, extracting a clean rotation signal from all the other things going on is a major challenge. But it's worth the effort, because understanding Betelgeuse's rotation could unlock another piece of the puzzle. It could explain some of the star's weird behavior. It could help us predict what the star will do next. And it could teach us about how rotation affects stellar evolution in general, which has implications for understanding stars throughout the universe. Now, here's a thought experiment for you. Imagine you could travel to Betelgeuse. I know, it's impossible. The distance is too great, the radiation too intense, the gravity too strong. But humor me. Imagine you could somehow exist near Betelgeuse and observe it up close. What would you see? Well, first of all, you'd be overwhelmed by the sheer size of the thing. If you were at the orbit of Earth around Betelgeuse, you'd be inside the star. You'd be surrounded by glowing plasma, hot enough to vaporize any material object instantly. The star would fill the entire sky. There would be no star to look at, you'd be inside it. But let's say you could somehow survive and observe from a safe distance, maybe from where Jupiter orbits our sun. What would you see then? You'd see a massive roiling sphere of red-orange plasma. The surface wouldn't be uniform. You'd see massive bright spots where convection. Cells are bringing hot material to the surface, and dark regions where the material is cooling and sinking back down. These features would be changing, evolving over days and weeks. You might see material being ejected from the surface, forming plumes and jets that extend far into space before cooling and condensing into dust. You might see oscillations, the entire star expanding and contracting, breathing like a massive cosmic lung. You might see shock waves rippling across the surface, triggered by instabilities in the interior or by collisions between different convection cells. And the light would be intense, overwhelming. Even though red supergiants are relatively cool by stellar standards, Betelgeuse's surface temperature is only about 3,500 Kelvin, compared to the Sun's 5,800 Kelvin. The sheer size of the star means it's putting out an immense amount of energy. Betelgeuse is about 100,000 times more luminous than the Sun. All that energy has to go somewhere, and it goes into heating the surrounding space, driving stellar winds, and creating the complex circumstellar environment we've been talking about. Now, back to reality. We can't visit Betelgeuse, but we can observe it with increasingly sophisticated instruments. And every new observation, every new data point, every new measurement is like adding another piece to a massive cosmic jigsaw puzzle. One of the most exciting recent developments in Betelgeuse research is the use of interferometry to create incredibly detailed images of the star's surface. Interferometry is a technique where you combine light from multiple telescopes to effectively create a much larger telescope. It's like using several small telescope mirrors to simulate one giant mirror. Using interferometry, Astronomers have created images of Betelgeuse that show features on the star's surface with unprecedented clarity. We can see individual convection cells. We can track how they evolve over time. We can measure the temperature differences between bright and dark regions. We can even start to create maps of the star's chemical composition, showing where different elements are concentrated. These observations are transforming Betelgeuse from an abstract concept, a red supergiant star, into a real, tangible object that we can study in detail. It's like the difference between knowing that a distant country exists and actually seeing satellite photos of its cities and landscapes. Suddenly, it becomes concrete, real, specific. And the more detailed our observations become, the more questions we can ask and answer. Where exactly is mass loss occurring? Is it uniform across the star's surface, or concentrated in certain regions? How do the convection cells interact with each other? What role does the star's magnetic field play in shaping its behavior? How does material flow between the different burning shells in the star's interior? Each of these questions can be addressed by careful observations combined with theoretical modeling. And each answer brings us closer to understanding not just Betelgeuse, but red supergiants in general, stellar evolution as a whole, and ultimately, the life cycles of the matter that makes up everything we see, including ourselves. Speaking of which, let's talk about nucleosynthesis, the process by which stars create heavy elements. This is one of the most profound insights in all of science, and it's directly relevant to Betelgeuse. In the first few minutes after the Big Bang, the universe created hydrogen, helium, and tiny amounts of lithium and beryllium. That's it. Every other element, carbon, nitrogen, oxygen, iron, gold, uranium, every single element heavier than beryllium, was created inside stars. In main sequence stars like the Sun, hydrogen fuses to form helium. In red giants, helium fuses to form carbon and oxygen. In massive stars like Betelgeuse, the fusion chain continues. Carbon fuses to form neon and magnesium. Neon fuses to form oxygen and magnesium. Oxygen fuses to form silicon and sulfur. Silicon fuses to form iron and nickel. But the heaviest elements, things like gold, platinum, uranium, can't be formed through normal fusion. They require even more extreme conditions. They're created in supernova explosions through a process called rapid neutron capture, or our process nucleosynthesis. Here's how it works. When a massive star explodes, the shockwave creates incredibly high temperatures and densities. Neutrons are flying everywhere. Some atomic nuclei capture these neutrons, one after another, in rapid succession, building up heavier and heavier elements. This happens so fast that the nuclei don't have time to decay between neutron captures. As a result, you can build up very neutron-rich, very heavy nuclei. After the explosion, these neutron-rich nuclei decay, shedding excess neutrons and transforming into stable heavy elements. That's how you get gold, platinum, and uranium. That's how you get the exotic rare earth elements. That's how you get about half of all the elements heavier than iron. So when Betelgeuse explodes, it will be creating new elements. It will be forging gold and platinum in unimaginable quantities. It will be scattering these elements into space, where they'll eventually be incorporated into new generations of stars and planets. The iron in your blood was created in the core of a massive star and scattered by a supernova explosion. The calcium in your bones was created the same way. The oxygen you're breathing right now was forged in a star. You are made of stardust, literally. And Betelgeuse will continue this cosmic cycle. When it explodes, it will enrich the interstellar medium with fresh, heavy elements. Those elements will mix with hydrogen and helium gas, form new molecular clouds, and eventually give birth to new stars and planetary systems. Some of those planets might harbor life. And if they do, that life will be made partly from atoms that were once inside Betelgeuse. That's the cosmic cycle. That's how the universe recycles matter. That's how stars give birth to planets and life. And that's why studying stars, like Betelgeuse, matters. We're not just studying astronomy, we're studying our own origins. We're tracing the history of the atoms that make up our bodies back through billions of years of cosmic evolution. Now, let me ask you something. Does knowing this change how you think about yourself? Does it change how you view your place in the universe? For me, it's one of the most profound realizations in science. We're not separate from the cosmos. We're not observers looking at the universe from the outside. We're participants. We're part of the universe. We're what happens when the universe becomes aware of itself. Every breath you take involves oxygen atoms that were forged in stars. Every time your heart beats, iron atoms created in supernova explosions carry oxygen through your blood. Your DNA, the molecule that encodes your genetic information, is built from carbon, nitrogen, oxygen, and phosphorus, all created in stars. You are a collection of stardust, temporarily organized into a pattern capable of thinking, feeling, and wondering about the universe. And Betelgeuse, that red giant star in Orion's shoulder, is in the process of creating more of those atoms. Right now, at this very moment, nuclear fusion in Betelgeuse's core is transforming lighter elements into heavier ones. Atoms that will one day be part of future planets, future life forms, future beings who will look up at their night sky and wonder, just as we do. That's the big picture. That's what this is all about. Yes, we're fascinated by the specific details of Betelgeuse's behavior. Yes, we want to understand the physics of red supergiants and supernova progenitors. Yes, we're excited by the prospect of witnessing a nearby supernova. But underlying all of that is a deeper current. We're trying to understand our place in the cosmic story. We're trying to comprehend how we came to exist, what we're made of, and how we fit into the vast ancient universe around us. And you know what? That's not just science. That's also philosophy. That's also spirituality, in a sense. Not in the supernatural sense, but in the sense of connecting with something larger than ourselves, something profound and meaningful. When you look up at Betelgeuse tonight, you're not just looking at a star, you're looking at your cosmic heritage. You're looking at a forge where the elements that make up your body are being created. You're looking at a future source of stardust that will, billions of years from now, be incorporated into new worlds. That's humbling. That's awe-inspiring. And that's why we study the stars. All right, let's bring this back down to Earth, or rather, back up to Betelgeuse, and talk about what we can expect in the coming years. Because the Betelgeuse story is far from over. In fact, we might be entering the most exciting chapter yet. Astronomers are planning extensive observing campaigns to monitor Betelgeuse continuously. New instruments are coming online that will allow even more detailed observations. The James Webb Space Telescope, with its incredible infrared capabilities, could potentially peer through dust and see features of Betelgeuse that visible light telescopes can't detect. The upcoming extremely large telescope's massive ground-based observatories, with mirrors 30 to 40 meters across, will be able to create even more detailed images of Betelgeuse's surface and track changes on timescales of days or weeks. And perhaps most excitingly, we're developing better theoretical models. The 3D hydrodynamic simulations I mentioned earlier are getting more sophisticated. Researchers are incorporating more physics-magnetic fields, radiation transport, detailed nuclear burning networks into their models. These improved models will let us make better predictions about what Betelgeuse will do next and how to interpret the observations we're making. There's also growing interest in studying Betelgeuse at wavelengths other than visible light. Radio observations can probe the circumstellar envelope. Infrared observations can see through dust and measure temperatures. X-ray observations can detect high-energy processes happening near the star. By observing Betelgeuse across the entire electromagnetic spectrum, we can build a complete picture of what's happening. And then there's the waiting. Because eventually, whether it's next year or in 100,000 years, Betelgeuse will explode. And when it does, every telescope on Earth and in space will point toward Orion. Astronomers will work around the clock, monitoring the supernova's evolution minute by minute. Data will pour in at rates never before seen in astronomy, and we'll witness and study a nearby supernova explosion with detail and precision that was impossible even a few decades ago. That supernova will be a watershed moment for astrophysics. It will test our theories of stellar evolution, supernova physics, and nucleosynthesis. It will provide data that astronomers will be analyzing for decades. And it will be a cultural moment, too, a shared human experience, as people around the world look up and see a new bright star in the sky. But here's the thing, we don't know when it will happen. And that uncertainty is part of what makes this so fascinating. Every time Betelgeuse does something unexpected, another dimming event, a change in pulsation, a new surface feature, astronomers wonder, is this it? Is this the beginning of the end? Or is this just more normal behavior for a weird star? Living with that uncertainty is part of the adventure. It keeps us watching. It keeps us engaged. And it reminds us that nature doesn't follow our schedule. The universe does what it does, when it does it, and we're just along for the ride. So what can you do? Well, for one thing, you can look at Betelgeuse. Go outside on a clear night. Find Orion, 3 bright stars in a row forming the belt. 4 bright stars forming the corners of a rectangle around the belt. Betelgeuse is the reddish star in the upper left corner of that rectangle, Orion's shoulder. Look at it. Really look at it. Think about what you're seeing. You're seeing light that left that star 650 years ago. You're seeing a massive red supergiant in its death throes. You're seeing a future supernova. And then think about this. The next time someone asks you, what's new in astronomy? You can tell them about Betelgeuse. You can explain that we're watching a star that might explode any day now. You can share your knowledge of stellar evolution, supernova physics, and the cosmic cycle of matter. You can be an ambassador for science, helping others understand and appreciate the universe we live in, because that's ultimately what this is about. It's not just about accumulating knowledge for its own sake. It's about sharing that knowledge, spreading the sense of wonder, helping people see the universe in a new light. Science is a human endeavor, and it's most meaningful when it's shared. So share this story. Tell your friends about Betelgeuse. Take them outside and show them the star. Explain what's happening and why it matters. Plant the seed of curiosity in someone else's mind. You might inspire the next generation of astronomers. You might change someone's perspective on their place in the universe. Or you might just have a meaningful conversation about something bigger than everyday concerns. And that's valuable. That's important. In a world that often seems focused on trivial matters, taking time to contemplate the cosmos, to think about dying stars and supernova explosions, and the origins of matter, that's a form of intellectual and spiritual nourishment. It reminds us that we're part of something vast and ancient. It gives us perspective. It connects us to the long sweep of cosmic history. So as we wrap up this journey through the Betelgeuse mystery, I want to leave you with a challenge. Over the next week, make time to look up at the night sky. Find Betelgeuse. Spend a few minutes just looking at it, thinking about what you've learned. And then, if you want, share that experience with someone else. Teach them about the star. Tell them the story. Pass on the sense of wonder. Because in the end, that's how knowledge spreads. That's how culture evolves. That's how we, as a species, come to understand our place in the universe. One conversation at a time. One shared observation at a time. One moment of wonder at a time. Betelgeuse is out there right now, burning fiercely, ejecting material, pulsating irregularly, doing whatever it is that dying stars do in their final millennia. We can't control when it will explode. We can't speed up the process or slow it down. All we can do is watch, wait, and prepare. But in the watching and waiting, we learn, we discover, We grow in our understanding, and we connect with something larger than ourselves. That red star in Orion's shoulder is more than just a point of light. It's a connection to the cosmos. It's a reminder of our stellar heritage. It's a preview of a spectacular cosmic event that may unfold in our lifetime. It's a laboratory for studying extreme physics. It's a source of inspiration for scientists and amateur astronomers alike. And now, having spent these hours together exploring the Betelgeuse mystery, you're part of that story. You know what's happening up there. You understand the science, the observations, the theories, the implications. You're equipped to follow along as the story continues to unfold. So keep watching Betelgeuse. Keep learning about it. And when it finally does explode, whether that's tomorrow or 100,000 years from now, someone somewhere will look up and understand what they're seeing because of the knowledge you've helped spread. Thank you for joining me on this journey through the Betelgeuse mystery. Keep looking up, keep wondering, and never lose that sense of awe at the universe we're privileged to inhabit. The cosmos is vast, ancient, and full of wonders. Betelgeuse is just one of them, but what a wonder it is. Clear skies, everyone. And may we all be fortunate enough to witness the light show when Betelgeuse finally reaches its spectacular end.